So I don't think I'm the only one in the room that was involved with UNAVCO, and it consisted of 4 GPS receivers and a few people. It's grown quite a bit, and I don't think cyberinfrastructure was decades from having been invented yet. But we now need to combine space technology and cyberinfrastructure to understand earthquakes. And here's an image of the San Andreas Fault, an airborne image. You can see it from space. It's the major plate boundary fault, but there are many other faults in California that are deforming and moving at about, across the plate boundary, about 48 millimeters a year, and across the San Andreas Fault, here's another view of it, at about 34 millimeters a year. This is Wallace Creek, which is an offset stream, and we can measure the paleoseismology record that way by looking at offset streams, and also then by using GPS to measure how the crust deforms over time. So back in the day when I had a budding scientist inside me who's now 14, we ran around with tripod GPS receivers. We still do that some. We collected data, we bent back, and we processed it by hand and studied what the Earth was doing. So here is the Northridge area. We said there was a blind thrust fault in that area, and the region was being compressed. The trees would be moving forward here, and the GPS, by measuring that, we could infer which was going on in depth. Now, the Northridge Fault was a blind thrust fault. The Sierra Madre Fault is a thrust fault that is exposed at the surface. And on this right slide, there are leaves in the fault zone to give you a sense of scale. These are very discrete fault zones, even though it runs the length of the mountains. And so we can infer what the faults are doing fairly well using elastic and viscoelastic processes. So then the Northridge earthquake occurred on that blind thrust fault that we had identified. It was a magnitude 6.7 earthquake. And it turned out it was kind of difficult to go out and collect GPS data when there had been landslides. These mountains here on Oak Ridge grew about 40 centimeters in the earthquake. That's a projection of the fault onto the surface. And in the upper figure, we show a radar interferogram. And that bullseye shows where the maximum uplift was as a result of the Northridge earthquake. So now we have thousands of GPS stations up and down the west coast of the United States. We have tripods that are drilled down into the ground and are permanent. We have daily solutions, and we can look at the quality of those daily solutions and mark them red or yellow as they change state over time. Green is no state change. And we get a nice velocity field. If we plot it relative to the San Gabriel Mountains, we can see a flow around the San Gabriel Mountains across the plate boundary of about 48 millimeters a year. We see compression across Los Angeles. And if we expand those GPS stations, we can look at the time series. This is a station that moved in the El Mayor-Cucapa earthquake, which was in Mexico, but it's a long way from that fault, near the San Andreas Fault, and it actually showed a lot of post-seismic motion as well, which is surprising. So our goal these days is to integrate all these data types we've been talking about, spaceborne and airborne radar data, GPS data, which give us position, time series, and velocity, seismicity, and faults, which give us the location and geometry of faults and the slip parameters on those faults. We want to integrate those in a modeling environment, which is done on the front end through a web interface, a web portal. And people can bring up things like UAVSAR radar interferograms, plot cross-sections through them, and see slip-on faults. This is a product of doing that for the El Mayor-Cucapa earthquake, which again was out in Mexico. But there was a lot of creep on the faults to the north, on the Superstition Hills and the Imperial Faults and the Yuha Fault. We see the interferogram as well as the creep events on the faults. We also work on producing earthquake forecasts using pattern informatics of seismicity. On the left is a coarser forecast. On the right is a finer, more recent forecast. And we now can do movie loops over decades showing how those earthquake hazard maps change over time. And we want to study interacting fault systems. And so we're looking here at the Hector Mine earthquake. On the left, these two faults on the right panel is the Landers Fault. And we want to see how earthquake faults interact by putting them into finite element models and other simpler elastic models. And then we need basic tools to just look at things like seismicity over the data that we have, so we can create KML movies of seismicity to see how the seismicity correlates with other features we see in GPS or the radar data. And we have simple tools like a moment magnitude calculator, which gives us a magnitude based on the area and slip on a fault. And of course, as the magnitude gets larger, the area and slip on the fault gets much, much larger. This isn't even to scale here. And then we all want to automatically produce data products when earthquakes occur. So we do this for every earthquake above magnitude 5 globally. And the reason is so that when an earthquake happens that we're very interested in, all those processes are in place and are automated. This is the Virginia earthquake. It shows about 7 millimeters of uplift over a 3-kilometer area. And you can play with these tools then on quakesim.org.